Hi everyone, my name is Lukas. I'm a founder and CEO of TACEO. And before we start, I just want to make sure we're all on the same page. So I think you would all agree with us that even if we make blockchains scalable and if we solve interoperability, they are not commercially viable. So there's still a crucial piece missing. It's infrastructure, and we call it like private compute. And at TACEO, we believe that coSNARKs will play a very crucial role into delivering private computation on blockchains. So I just want to make a quick temperature check. Who of you heard of the term collaborative SNARKs, or short coSNARKs? Yeah, I guess there's like 10 people. That's like 9 more than at ETHDenver last year. So slowly we go. Now, before we're talking what are coSNARKs, I want to make sure why do we need them. And for this, let's look back at the Web3 state models that we have today. Everybody is familiar, even outside of this room, with the public state model. So we got this from Ethereum, basically a programmable blockchain. So we have this now for 10 years. And the great thing about it was that we did get composability of this state for free. So you couldn't even construct really a public state without being composable. And with composable, I mean like what you see in DeFi, these Lego building blocks that you can stack together. You can call other smart contracts without worrying that you do not have access to the state. But of course, it came with this huge downside of having everything public. And thanks to very talented and gifted teams that were brave enough to build in the privacy space, we have now what we call private state. Unfortunately, it's not the case like with public state that it comes with a default composability. So the private state we see today that is mostly CK-based lacks some of the composability features we are so used to from public blockchains and which make them so interesting. Now, to make private state composable, what do we need? We, of course, need verifiability. And what we have to solve here is we have to compute on multiple private states without leaking them to anybody. And the first one pretty much looks like CK. Verifiability, we know this for a few years already. It's great to do this with CK. And the second problem statement is a textbook example of the definition of secure multi-party computation, or short MPC, which we already heard from the talk world today. So the easy solution to create composable private state, which is also known as private shared state, is just to combine them both. And that's essentially what collaborative SNARKs are. Combining these two subfields of cryptography, CK and MPC. Now, thankfully, there was a paper in 2021 from Dan Bonnet and Alex that showed us how to collaboratively compute the proof. And what this means is that no prover gains knowledge about the witness data, so about the private state. And their approach was just to run a CK prover in an MPC environment. So really straightforward, combining these technologies. This wouldn't be a paper in its own, like this would be too easy. What they really showed in this paper was that unintuitively, the overhead that you create by combining these two complex technology is not a multiplication of the overheads that we have from CK and MPC. So let's take, for example, CK. What's the overhead today? Probably in the range between 100x and 10,000x, depending on the use case and the hardware, and et cetera, et cetera. And similar for MPC, maybe a bit lower. You would think that if you combine those two technologies, you end up with a multiplication of the overhead. So like really order of magnitude 5, 6, and then you're getting slowly screwed. But what they could show in this paper is that you can add MPC to CK with essentially no overhead. So a statement of the paper was, whatever you can prove with a single prover in zero knowledge, you can also do in a collaborative fashion with little overhead. Of course, like in every paper, there are some detail left for the reader to figure out, and this is getting nasty at some point, but we'll see how we solve that. Now, before we dive into a bit more of the practice of collaborative SNARKs and what we have built, why do we need them like with real-world applications? For example, we heard this today already in some talks. They're very good for private proof delegation. So think about very complex zero-knowledge proof client-side that you might want to outsource, or like in the world case, you have very limited resources because you're running on very old phones. You can now have another option between like doing client-side proving or doing this transparent delegation where you have no security and privacy for your data. You can use collaborative SNARKs to privately outsource your proof generation with the same speed that any server-side CK has. And this is not really a net new application, it's just an improvement of existing zero-knowledge proof generation. But the other three are like really private shared state application that you cannot build with CK alone. So this is, for example, private dark pools, like think of a private decentralized exchange, where you have to combine, for example, two orders in a secret shared fashion. Or you want to build on-chain games that have some asymmetric information, so like think of fog of war, or from the talk earlier, private CKML. Now, enough from like theory and examples. What have you built? So why are we here at NoirCon and not at any other talk, any other event? Because we have built what we call coNoir, which is an MPC VM plus an MPC proving backend for Noir. Like, why do we need both? We will see in a minute. But basically, like, the MPC proving backend for Noir is wrapping the ultra-hung prover, in this case, into an MPC environment. So we re-implemented the whole ultra-hung, every step and every component. Maybe some learnings here was like the linear operations in the prover, like the multiscalar multiplications, for example, are very easy to do in MPC. You can just use basically the native CK version and you are as fast. What gets a bit tricky is the sum check part of the ultra-hung prover, because here there are nonlinear computations, and so this is the most complex part if you rebuild it in MPC. And a very nice feature again for collaborative SNARKs is you can use the same verifier as traditional SNARK. So you don't have to build any new verifiers, they're all compatible. So in this case, for example, with Barettenberg, which is Aztec's proving backend. Now, we also had to build a full MPC virtual machine. And the reason is because we have to do the witness extension also in MPC. Witness extension is a part of the zero-knowledge proof generation that is usually doesn't get a lot of attention. Because what it does is basically doing a plain computation of the program, so just a regular program execution. And if you're doing this like in public or client-side, this is the part that consumes less resources, so you don't worry too much about it. But like, if you want to have truly private shared state, also this witness extension, because here we're also using the private data, has to be performed in a confidential environment. And that's why you have to do the whole part in MPC. And as Noir allows arbitrary programs, we also have to allow arbitrary programs. And that's why you need general purpose capabilities for confidential compute. And this leads us down to the rabbit hole of building a whole MPC VM. Just a side note, why also in the paper they omitted this part a bit, because if you're just using collaborative SNARKs for private proof delegation, you kind of can, you don't have to do this, you just do the witness extension locally because it's less resource constrained, and do just the heavy part, the heavy lifting than in MPC. But it's essential if you want to have private shared state. Now, a bit into the details, how is coNoir deployed? So how does this really look like? From a developer's perspective, you just write regular Noir programs, so you don't have to learn any new language. There's no MPC language you have to learn, you just have to know Noir. So on the left we see, for example, a program where we have an inclusion proof done with a Poseidon 2 hash function. And the Noir stack then compiles the program, and we just have to interpret it differently. First, with our MPC VM, just interpret the different variables that are secret shared in a different format, and then execute the whole program in our MPC VM, and then in the end produce a collaborative SNARK, so a proof about the computation. And what you see here with Alice and Bob is they are the users in this system, and they do the secret sharing. It's a technique from MPC, so that you split up your witness data into secret share and add randomness client-side. This is important, like that you do this client-side, otherwise you would leak all your information. And then you directly send the secret shares to the MPC network, which take this as an input for the program, the coNoir program. And what you get out is like you're getting 3 secret shares as a result out, and you combine them. For example, here it's called Charlie, but this is very abstract. You could, for example, think this is a smart contract, and the smart contract then gets the output of the computation and a proof. So this is here depicted with coSNARKs, and this is then verified in the very traditional way with a verifier that already exists in the ETHDenver ecosystem. So where are we in the practice? How much of this is implemented? How fast is it? So since last week, we have the first benchmarks out. So this is the first time we show them here. This is for, the first row is for a Poseidon 2 hash function, so a CK-friendly hash function that is used a lot in the Noir and ETHDenver stack. And you see like the MPC VM, this is basically what I told you about witness extension, and the MPC proof generation is the actual collaborative SNARKs generation. On the right hand, we have the Noir program, so if you do it just with CK. And from the absolute times, this is quite okay-ish already. Like if you look at the Poseidon call, this takes roughly 100 milliseconds. And if you have like Merkle tree inclusion proofs of depth size 16, you have 1 second, and like for 32, it's 2 seconds. But we're kind of still a bit off from the CK only times. And this is mainly due to because we just worked on feature richness for coNoir so far and not on performance. So we have implemented also what we call coCircum, which is the same as coNoir, but for Circum, which is of course not that feature rich. And there we could show that you can approximately match the CK proving times. So we would expect that these times on the left come very close to the times on the right over time. And to get there, we focus in the next couple of months on performance. And this means we will implement the remaining black box function, which basically pre-compiles in Noir. We have already 3 implemented, 17 left to go, and do more general purpose improvements. Thank you. Here is a link to the GitHub repo. It's all open source, so if you want to try it out, just give it a shot, and yeah, just hit me up after the talk and we can help you set up everything.
Thank you, Lukas, for an excellent talk. Lukas, besides being a founder and CEO, is also a former cryptography researcher and also former pro cyclist, which I found very interesting. But yeah, if you guys have any questions for Lukas, I'm happy to hand you the mic. If not, I can start off with one. Maybe you could talk high level about the trade-offs between privacy, scalability, and performance with TACEO.
So I would say with TACEO, it's all about privacy. Where you have probably some trade-offs with scalability is you can choose your underlying MPC protocols. So there are MPC protocols for different trust assumptions. And you can, of course, go way more decentralized, or you can go less parties. You have an honest majority, dishonest majority, so you have some levers here that you can pull.
And maybe a follow-up, how do you see this playing out with like consumer applications using TACEO and maybe Aztec and other networks to try to solve different scalability problems, performance problems?
I would assume that first people look very heavily at the performance, so they want to have privacy, but it doesn't have, like, it's not allowed to cost too much, so they would probably be fine with a setup that is like not decentralized with 100 or 200 nodes. They're maybe good with like a few nodes that run in TEs, for example.
And how do you see maybe these types of solutions evolving over time, especially on the consumer side?
On the consumer side, could you double click? What do you mean?
Maybe at the institutional level, let's say, how people may interact with TACEO, with Aztec, with these types of networks.
I think they will like fade away a bit into the infrastructure perspective, and people don't really know what they are working on or whatever. They just know the properties they get from the system, like they know that they get privacy, that they know they get some sort of some kind of decentralization, and probably have a feeling how strong they are, but not anymore.
What do you see as some of the blockers for that reality?
I think the concept that we propose are extremely difficult to grasp. Once from a technical side, like DevX can be much better, but also like building business models where data is not the center. I think nobody's trained for that, and so having like creative people, builders, to think outside the box that they don't have to use the data to make money will take some time.
What other ways could people center their business on outside of data? Do you guys have any ideas at TACEO that you feel like people building on TACEO would be excited by?
Yeah, for example, like take World. They don't use your data, they don't store anything of your iris code and so ever. They cannot ever monetize this, so they have to find different ways to monetize their tech stack, and I think we'll see some creativity there in the coming months.
Awesome, thank you. Cool.
You had mentioned that with CIRCOM, you guys hit kind of parity with just the ZK and then the MPC proof. But you mentioned how SumCheck is where like the great cost is. You don't see, we probably won't hit like equal for the MPC proof with UltraHonk though, right? I imagine there will be some overhead with the MPC proof. Like, I guess kind of, how do you see the overhead there with the actual MPC network in UltraHonk?
Yeah, so if we can like rely on a very good network, I would see that the overhead is very minimal. Okay. Why we have such a huge overhead, for example, in the SumCheck for now is like people build differently in CK, not with the constraint of MPC in mind. So you have a lot of multiplicative def in the SumCheck, which is not needed. You can rebuild it, and that's what we are currently doing. So making more multiplications in the same round, so you don't have too many communication rounds in the MPC protocol, because this often gets then the bottleneck.
Okay, yeah, makes sense.
Hi. In general, MPC systems still suffer from Byzantine generals problems as well too. So do you see a future where you would collaborate with other crypto economic systems and integrate this as a providing service where you'll have other slashes, other things to prevent civil attacks in the future?
Definitely. Like, as blockchains, we all have the collusion problem. And I think one way is like putting the node operators of the coSNARKs in TEs gives quite a good assurance already. But again, of course, you can stack them and, for example, use eigenlayer for the liveness property. And I think then you can build a really robust system if you stack those technologies together.
Cool. Any other final questions? All right. Thank you, Lukas and TACEO.